that it should have recommended to everybody to listen to you guys, Yifei and Philipp. I think you guys are coming up next. Nice. Where are you guys located again?
San Francisco.
You're in SF, right. I think we did a big event with you guys not too long ago, which I heard was a massive success. And, well, I'm stoked to see what you guys are up to today. The spotlight is on you guys.
Thanks for the intro, Adam. Really glad to be here. So today in this session, we're going to talk about RAG. And just a quick introduction. My name is Yifei Feng. I'm an EM at Anyscale.
And I'm Philipp. I'm the CTO at Anyscale.
First, just a quick overview of what we're going to be talking about. We'll walk you through our journey building a retrieval augmented generation application. So we'll talk about the architecture we used and how we evaluate our system, as well as some of the experiments we ran and the results we had. And after that, we'll also talk about the challenges we ran into in each of the steps in building this RAG application and the solution that we had. So the RAG application we want to build is this question-answer assistant for Ray. So what is Ray? Ray is this open source library. The goal of it is really to help scaling your AI and Python application extremely easy, fast, and cost efficient. So you can focus on kind of building your AI and Python application instead of dealing with how to scale up your system. So it comes with a suite of application library that handles different part of your life cycle in developing your AI Python application. So for data processing, we have read data and retrain for train your model, as well as reserve for deploy your model. So it kind of has become this de facto go-to tools for scaling up your ML workloads. As you can see here, that we've seen it being adopted across different companies, all sorts of applications. We're really excited to see the enthusiasm of the community, and we really want to build something to help everybody in the community to learn about Ray and adopt Ray in their application. So that's why we really want to build this question and answer assistant. So you might ask, why don't we just use a simple LLM? They seem to be pretty powerful nowadays in terms of doing question and answer system. So there are a few problems with this approach. First is these LLM are kind of trained on older data. And in our case, we're continuously updating our documentation as new features are released. Second, general purpose LLM, they don't really include your private data. So for example, if you have user data or intellectual property you like to include in your answer, they will not have access to those. And third is hallucination is a common issue of this general purpose LLM. And in our case, we definitely don't want our assistant to come up with some random code snippets. Okay, so what's our solution? We can provide these models with context. So in our case, a lot of information for the answer of this question are already in our documentation, but we really need to stitch all these different pieces together. So here I want to give an example. This question is a real question from one of our users. The user asked, I want to use ray.wait. What happened if the task failed? Okay, just to give some context here, ray.wait is what you call when you want to block remote asynchronous call until you get the result of it before you proceed with your program. So to really answer this question, you need two parts from our documentation. One is to understand how does ray.wait work, and the other is to understand how does ray handle fault tolerance. So this is a good example of how such system can find these two different pieces of information, put it together in a reasonable way, and present that to the user. So I'm going to pass the mic to Philipp to talk about how we build this RAG application.
So let's now go over how we build this application. And this is the architecture of the retrieval augmented generation. It's both a very simple paradigm, but also incredibly effective at putting more knowledge into LLMs. So the query comes in, and then we look up the most similar or relevant documents to the query from some database. And then we get the top results, and we put them into the context of the LLM, and then return the response to the user. In practice, often what is used here for most relevant is a similarity, vector similarity. So we take all the documents we have, and we use an embedding model to calculate vectors, and then we store those into a vector database. And then when the query comes in, we embed the query with vectors, and then we look up the most similar vectors from the vector database, and then use those documents as context. And in practice, the embedding dimension is often 512 to 1,500 dimensions. So let's now dive a little bit more into how we can create the vector database. So everything starts with the data sources. In our case, that is either the RAG documentation or the RAG blog or the RAG book. And then we load all those documents, and then we have to chunk them up into smaller chunks. That is because the embedding models are typically most effective at smaller chunks, like a single paragraph that only contains a single topic. And then we run the embedding model to convert all those chunks into vectors. And then we index those into a vector database. And the vector database can efficiently represent those vectors and can efficiently support queries over those vectors. So we can get the most relevant documents. The documents, as you see below, are often represented as a tuple of text and then the source, so we can link the user back to the information and then the embedding, and that gets stored into the vector database. So let me dive a little bit more into this chunking, because it's actually very crucial and it always depends on your data on how you should do the chunking. So oftentimes we have to deal with HTML documents, like the RAG documentation or the RAG blog. And so we basically pass the HTML and then we split it up into sections. For each section, we keep a link to the section with the HTML anchor. And then if the section is long, we will split it further up into paragraphs or code snippets, and also try to keep those paragraphs together and try to not split up the individual code snippets, so the LLM can be most effective at answering the questions. And then after we have created the vector database, we have to do the retrieval. So for the retrieval, the query comes in, and then we embed the query with the embedding model. We get the query embedding. That is a vector. And then we pass that over to the vector database index that we built, and then we get the top K documents from that. The K is, of course, a parameter that we can choose, and then we feed those into the LLM. So that's the next step. We take those top K documents, feed them into the LLM together with the query, and then we generate the response for the user. So there's a bunch of parameters that I've been talking about, and we need to select those parameters. So these include what concrete embedding model am I going to use, which LLM am I going to use, how large are my chunks going to be, what chunking strategy am I going to use, and then how many top K chunks do I put into LLM. So we need a robust way to evaluate which of these is going to be the best. Oftentimes we start off with just trying it out and trying a few queries, but then as you get more serious and iterate on the application, you also want to have some way to check that the application still works after you do more changes. So you should start building a data set of those queries. What we did is we built, from the community questions, we built a data set of about 200 questions, and then we hand annotated them with the sources of the chunks in the documentation that answer those questions. And then there is basically two ways how you can use this data set to do the evaluation. One is component-wise. This is very similar to unit tests in traditional software engineering, where you take a single component of the system and then you test that. For example, you could test the retrieval mechanism by just running the retrieval and then checking if the underlying documents that you annotated your query with are found by the retrieval. Or you could test the LLM part by fixing the context, the ground truth context you put into the LLM, and then checking how good the answer is. You can also do end-to-end evaluation. This is kind of like an end-to-end test in software engineering, and then make sure that the overall system works end-to-end. So you feed the query into the system, and then you run it, and then you get the response out. And then you do the evaluation on the response. So now the question is, how do I do the evaluation? Because, okay, you can do human evaluation where you check the response by hand, but this is not really scalable. So there are actually good techniques how you can do it in a more scalable manner by using LLMs as a judge for the evaluation. So let me talk a little bit more about that. So you can basically put the question and the context into the LLM and then say, I have just proposed answer by the system. How would you rank that on a score between 1 and 5? And also give your reasoning. And then you get, you can get answers like this one, where in this case, it's a very good answer. The LLM gave it a score of 5. and then the reasoning tells us what the LLM likes about it. And this works actually, while it does not replace human evaluation, it actually works pretty well in practice. And you can use that to automatically run, for example, if you make modification to the system, you just run your evaluation suite on your dataset, and then you get a good idea of whether things are working. So let's now dive a little bit more into the experiments that we ran to get the best parameters. And of course, the best parameters will depend on your own application, but we are going to share what we found. So what the experiments we ran were, first of all, we tested a number of chunks from 1 to 7, and then also the chunk sizes from 100 words to 700 words. And then we also tested the embedding model, starting with some widely used embeddings. Maybe you're aware of this, the Hugging Face leaderboard, where there's a bunch of those embedding models evaluated against standardized data sets. And so we took some of those, and we also took the OpenAI embeddings. And then we also evaluated against a bunch of LLMs, like GPT series from OpenAI, and then the Llama models from Facebook, and also Falcon 180B. So let me share some of the results with you. The first one is about chunking. So here you see at the top, we did the experiment both without context and then with context. So that shows, and as you would expect, with context is a decent amount better. And that shows that it's actually important to put in the context and to build the whole RAG application. Then we also did experiments with chunking. And there, for the overall quality, the end-to-end quality score, typically larger chunks are better because there's more information in there. But you also see in the retrieval score that the performance actually goes down as you increase the size of the chunks. That is because the embedding models actually get less effective at representing the information in the chunk if the chunks are too big. And then we also did experiments against the number of chunks that we feed into the LLM. And there, it's oftentimes more is better, but there's a limit because the LLMs have a limited context size. So we cannot exceed that size. And then at the end, when we took all the best results from everything, we got a pretty decent score of 3.6. We also tested this against a bunch of different models. So first of all, against embedding models. And there actually, it was a little bit surprising for us because the best model in the Hugging Face leaderboard is actually this model BGE large EN. But that was actually, for our application, not the best model. The best model instead was another open source model called GTE base. We also tested against the OpenAI embeddings, but they actually performed slightly worse than the best open source model. And then we also tested different LLMs. And as you would probably expect, GPT-4 is still the undisputed winner here with a score of 3.8. But GPT 3.5 Turbo, which is much cheaper, is actually also doing pretty well. And then the Llama 70B model is actually pretty close in performance to GPT 3.5 Turbo. So I'm actually very excited about all the progress in open source LLMs, and I'm looking forward to future open source LLMs that are going to do even better. And then maybe a little bit surprisingly, the larger model, Falcon 180B, was actually slightly worse than the 70B Falcon model. Okay, now that we talked about the application, let me talk about some of the challenges in building and deploying the application into production. So the first one is about scaling up. This actually hits you right when you start working on the application. Oftentimes you have a large number of data, and then also you need to compute all these embeddings, and that is pretty computation expensive and needs GPUs. And also you need to run all these evaluations, which often also takes a long time and is good to parallelize. So we chose to use RAG-data for scaling up the data pipeline. RAG-data actually makes it very easy to integrate all these different data sources. It supports Parquet files, JSON files, CSV, text files like HTML, images, TensorFlow records, SQL, and you can load those from different sources like a shared file system or a blob storage or a database. RAG-data was built from the ground up to support both CPU and GPU compute, and it can effectively use both of those together. So some of the computation often happens on the CPU, and then embeddings, for example, utilize GPUs, and RAG-data will make sure that the right resources are utilized, and we scale up CPUs and GPUs independently. It also has been built with first-class support for tensors, And it's actually the fastest and cheapest solution for this kind of offline inference on unstructured data. And if you want to learn more about it, I have a link to a blog post here where we do evaluation of different systems, and it has more information about RAG data. So RAG data was really helpful for implementing this data pipeline and then scaling up those embedding calculations. The second very important challenge is in the deployment. So we have actually many different components that we need to stitch together, like our embedding model, and then the LLM, and then also we do actually some more things like ranking, and then there's a bunch of operational challenges around this in terms of how you do logging, how you keep the metrics about request latencies and so on, and improving those. So we chose RAG to deploy the model. RAG is a production grade deployment model system built on top of RAG. And it supports some of the unique challenges that LLM applications have. One of them is being able to compose multiple models, like, for example, embedding models. Oftentimes you have need some sort of personalization. In our case, that was not the case, but many applications need that. And then you want to rank the results of your retrieval and then run the LLMs. Another very important challenge is low latency. Oftentimes, these LLM applications are assistants to users. So if it takes 30 seconds to get the answer, then that really makes it much less productive. So it's crucial that we get the response to the user as fast as possible. And RAG can help you with that by both efficiently and in a low latency way evaluating the prior model before the LLM is called. And then also for the LLM, RAG supports end-to-end streaming. So we can take the tokens as they appear and then form the response to the user and immediately start pulling the answer all the way to the user through WebSockets or other streaming ways. In addition to these LLM-specific challenges, there are some MLOps challenges that you have when building and deploying such an application. One is being able to upgrade the application with zero downtime as you evolve the model and the chunking logic and the index and the evaluation. Also being able to do canary rollouts to serve only some of your users, seeing how it performs, and then rolling back if there's a problem. Also, being able to do observability, like logging, to see what are the response, even having feedback from users, thumbs up, thumbs down, is the result good, and seeing what are the metrics, how's the performance doing, is very important. And then last but not least, RAG also supports efficient autoscaling and flexible resource allocation that can really help you bring down your costs. RAG is very convenient to develop in because it's just native Python development. It's very simple and flexible. You can develop on your laptop. You can iterate quickly, and then you can robustly deploy the application on, for example, Kubernetes. If you want to learn more about RAG, we have a blog post where we talk about how RAG can help you serve your AI application in production. So now Yifei is going to tell you a little bit more about how we can continuously improve the application. And yep.
Cool. So now you have deployed your application, and the next thing you want to do is maybe, hey, how do we incorporate all this feedback we get from user and improve it? So, okay, first you can do, as Philipp mentioned, is you can collect some of this feedback. So for example, collections like, hey, what kind of question our user are asking our system, and what are the chunk of context the vector database returned back, and whether user find this response helpful or not. There are a few things we can do here. One thing is we go back to our data source, in this context, our documentation, and see, hey, if you just need to improve our documentation. We might also want to retweak our existing system on some of the parameter that Philipp mentioned earlier. For example, rechunk, our documentation. And then we might want to rerun our data pipeline again to regenerate the vectors for the vector database. And another thing we can do is to really make our model more intricate here. So for example, we can fine-tune our embedding model. These off-the-shelf embedding models, they don't really have domain knowledge of, things that's specific to RAG, for example. So we can introduce some of that by fine-tuning the embedding models. And another really popular thing to do is to just retrieve the result based on you already know about the query. So basically what we're doing here is we are introducing a lot of new models here and there in our system to improve the quality of the entire system. And we'll need to keep iterate and retrain these models again and again as we're getting new data from our user. So how do we make this process really easy and really iterative and really fast? The tool we choose to use here is retrain. One great thing about retrain is that it integrates really well with all your existing deep learning framework. So you can choose whichever tools that you are already familiar with or really optimize on the hardware that you want to run, and mix match all of this across all of these different models. And to configure your scaling, it's also really, really easy with just one line of code, and you can scale it across CPU, GPU, even your customized hardware as well. And what retrain really shines is also its performance. It can really help you speed up this iterative process. So just to give an example, Instant Car is one of the retrain user, and they are using AI across the board for fulfillments, for recommendation, pretty much all sorts of different application. And they were able to run training 12 times faster on retrain and train on 100 times more data, which is very impressive result. Okay, so now we iterated a bunch, improved our model a lot using retrain, and our system is doing really well. Our users are flocking to this assistant, and we're getting tons of usages. And now we really want to think about how to keep our costs down. So the LLM part is really going to be the most compute intensive and costly part here. So what we did is we did a cost performance analysis across all sorts of LLM. And as Philipp mentioned earlier, it's not surprising GPT-4 did better than the other models, but it also comes at 47 times the cost of, say, Llama 70B models. And in a lot of situations, we might not need a really powerful model like GPT-4. Just to give a few examples, if user is asking a pretty straightforward question and the answer can be found just somewhere copy-pasting from the documentation, you probably don't need a model that can reason a lot, and some small open source model might be good enough in this case. Or if users asking, hey, can you give me a code example? You can use code Llama instead of GPT-4, and that's probably good enough. So what you really want to do here is something like introducing a classifier to do hybrid dynamic routing. Depends on the question folks are asking here. So what we did is we used Reserve to implement this hybrid routing. Reserve really make this kind of model composition extremely easy to implement. Another really good thing that Reserve can do is it can auto-scale these different models separately. So you only really pay the compute cost when you need the load. Okay, so another way to reduce costs is really switch to our open source model. And maybe you don't want to host this model yourself. And what we used is we used Anyscale Endpoint, which is an OpenAI API compatible platform that holds open source LLM into your application. So it's a pretty easy drop-in replacement. And also, inference for LLM is really a full stack problem here. So at Anyscale, we worked really hard to integrate optimization across the board. This is how we can offer the lowest cost for Llama 70B in the market right now. So at $1 per million token. So if that's something that you wanted to reduce your cost, that's something also great to try out. So I think that's everything we have today. We saw there are a lot of really great questions about the details of how we built the route application. We're of course happy to answer all of these questions at the end of the presentation. But if you're interested in a lot more details, I also encourage you to check out the blog posts here on the left. And it also comes with the GitHub source code for everything that we developed. So if you want to go check that out as well, maybe take that and adapt it to your RAG application, please feel free to do so as well. And on the right side, we also have a link for Anyscale Endpoint, and we're including not just Endpoint API as well as fine-tuning. And if you have sensitive data, you want to just deploy everything in your own environment, we also offer something like a private endpoint if you're interested in checking out. Thanks again for joining us. Happy to take any questions.
Thank you very much, guys. And yeah, we did the workshop on Ray, I think, so which was very hands-on, and that was excellent. So if anybody's on SF, it'd be great to do this again. We're flooded with questions. let's see. Wham says, which vector DB is used here?
So we used Postgres with PG vectors. That has been a great solution. We can leverage existing Postgres knowledge and using existing databases, RDS and other cloud databases, for example, support PG vectors. It won't work for like huge scale data, but for many use cases, I think it's a great solution.
From Manpreet, how do you select the embedding model, especially if your use case has multilingual content? And how important is the choice of the vector database for RAG?
So the embedding is chosen via this evaluation technique that I was talking about earlier. So we created a data set with ground truth sections, and then we used both the retrieval score as well as the end-to-end score. And there's much more detail in the blog post if you're interested in more into that. And then how important is the vector database? I would say if you have an existing database like Postgres that supports the use case, then that actually supports all the different indices that are widely used. So that will work. If you have very large scale use case, then there's also dedicated vector databases. So it depends on your use case.
This is Soren asks, I'm curious if you know examples where Elastic is used instead of vector DB, and what are the trade-offs compared to more traditional vector DB?
So I personally haven't used Elastic, but I know Elastic is definitely working a lot on making it a great database for vector DB stuff. I would say if you already have an Elastic database and your documents are already in there, then it's a very good way to check it out. It also allows you, I think, to combine vector search with keyword-based search, use the metadata and so on. So if you have an existing database where your documents are in, I would encourage you to try out if that also supports vector embeddings, then that will be a good solution. Otherwise, there's a decent number of dedicated vector databases.
Yeah, one more thread here is about not using vector databases, but instead to use sort of like more traditional knowledge graphs. Well, insofar as they already have the data that you're trying to index, I mean, this is consistent with your answer. You might as well just...
And also, if you already have an existing information retrieval system, it totally makes sense to try to plug that into your application and see how well that performs.
Yeah. Have you experimented with different retrieval algorithms? How do you think about retrieval in cases where semantic similarity is insufficient to identify the reference chunks best suited to your purpose?
So we mostly used embeddings, but what we also did is some amount of re-ranking. So after your query comes in, you can take the top maybe 100 documents, and then you can, based on the query, maybe based on the user, and based on some other context, you can select the ones that are the most relevant. For example, one thing we did is train our model on the RAG discourse, then mapping the query to the topic, like the library that the user is using, and then ranking those libraries higher. That can actually help. Yeah, it depends on your application, I would say, but there's a decent amount of also traditional ML techniques that you can incorporate here.
Yeah, we have a few questions here, both on quality and evaluation on one hand, and on the other hand, on chunking. So maybe we could take the chunking ones first very quickly. The chunk sizes, whether you're chunking words or characters, think was anything about how, could you explain how you broke down information into chunks for the with chunking?
So what we do first is, because we have structure from the HTML documents, we first chunk things up by section. That makes sure that there's no mixing between sections. And then what we do is we try to find good breaking points, like things like paragraph. We try to keep the code together, for example. It depends very much on the semantics of your document. The chunking is actually very important. Like if you cut a code segment in the middle, the LLM will get confused and the answer won't be as good. So I would say this is one place where I would spend a decent amount of time trying out different things, trying out your domain knowledge of your specific application, and then, yeah.
Anything else that you could say about the evaluation? So Ben Epstein is asking, how did you run the tests? What is a quality score? How do you define that? Why is 3.6 good? Quality score, retrieval scores. Many more people are asking how you got the retrieval scores.
So we used a scale from 1 to 5. That works pretty well. I've seen other people use like binary scores between 0 and 1, or 0 or 1. I think all of these can work pretty well. Too fine-grained doesn't make sense. Like 1 to 100 probably doesn't make sense. And then GPT-4, I would say, is still the probably best LLM to do the evaluation. Yes, much more information in our blog post, so check it out.
Yifei and Philipp, thank you very much for joining us today. This was an incredible talk.
Thank you so much.
Thank you for having us.
Bye.